Alright folks, it's time for another C++ tutorial video. Today we're going to talk a little bit about dynamic arrays and passing arrays to functions, as well as a couple of other function options which kind of creep up around this time when you're studying a new language. So you should be pretty familiar with arrays and using constant integers in order to create them. What's going to be really new today is the fact that we don't always have to have a constant integer to create our arrays. In fact, sometimes it's beneficial not to do so. These are called dynamic arrays. And in order to create a dynamic array, you have to learn a little bit about pointers because array names are pointers, and for dynamic arrays to be allocated, you get access to them via pointers. And so we're going to start off by declaring this integer n, which is going to be the size of our array, and asking the user to give this to us. So tell us how many whatever it is that you want. So we're going to do names. We're going to make a dynamic array of strings. In fact, I better go up here and add some string include. And after the user tells us how many they want, this integer n here, what we're going to do is create an array based on n. Now, there are some extensions that allow you to do this exactly like you do it for static arrays, but we're going to learn the kind of more standard C++ way. And so what you do here is you create a pointer to a string. To create a pointer to a string, you use the star. In fact, to create a pointer to anything, you use a star. And so int star is a pointer to an integer, string star is a pointer to a string. Here we're going to call this array names. Now, this is a pointer. Pointers are addresses. This thing is going to hold the address value of the array, or more particularly the first element of the array, and then we'll figure out what all the other addresses is based on that. What we're going to assign this to is a piece of dynamic memory that is allocated to us. We request that by using the new keyword. So in this case, string star names equals a new string, and then we tell it the size inside square brackets. So when we're dealing with arrays, static arrays, we can delete the star and delete this keyword new and delete the extra string here. But when you have a dynamic array, you need all three of these pieces. What's really, really great about this is that at this point, you can use this dynamic array just like it were a static array. The biggest difference is that n was something that wasn't determined at compile time, and it's determined at runtime instead. So you can still write for loops that kind of walk through every string in the array. You can read in values for all of these. You can output them if you want to. And this all works just like it were a static array. The biggest difference here is that the size is not determined at compile time. Instead, this size is determined at runtime, which is the biggest way that you know you're dealing with. Is this not showing up? Oh no, my console window is not showing up. Anyway, it does say tell us how many names you want. I'll say 5, and then it waits and echoes all 5 of these names for me. You guys cannot see it because my console window is not showing up, and so that is very, very sad. That's really it for dynamic arrays. One thing that would be really, really nice is if we could do something like wrap this input or this output maybe into a function. In order to do that, you do have to understand that the names of arrays are pointers. And so when we write a function for something like, hey, let's just output this array, in order to pass the array in, we have to pass in the pointer to the array. So we would pass in something like string star names here, and then it's a good idea to also pass in the size, even if you kind of know what the size is going to be. Once you get to the dynamic world, you're not going to know what the sizes are. This particular setup will work for whether it's a static array of names or a dynamic array of names. You could write this function one time and never have to write an output function for any of your string arrays ever again. So in this case, we're just going to use the same for loop that we were writing before, walk through all the indices of the array. They're the same as they were in the static arrays, and then output each of these names. Probably a good idea to put an indel down here. And then calling this, you just call the array name. So if you wanted to output all of the names in the array, oh, I deleted the wrong section. So if we read in all the names, and then you want to output all the names in the array, you call output array, you pass in the variable names and the size. This is not different. What's really weird about this is that this variable here, names, is a pointer. Pointers are address values. So what you're actually calling or passing by value is the address or the pointer. You're not copying all of these array elements when you pass this. You're only copying the pointer. What that does mean is that when you pass a variable of an array, when you pass an array name to a function, you can alter the individual elements in that array and it will affect main. This has implications for how you pass variables to things, and it brings up call by value and call by reference, which I'm going to tackle here in a second. The biggest point here, though, is that if you pass an array to some function, that function is probably capable of changing your array elements. It's a little bit of a note. So if somebody comes in here and writes names of 0 equals doc, okay, that will change the first element of whatever array was passed into this function to the word doc, whether you wanted that to happen or not. This was not a danger in our functions previously, and it has to do with the fact that what you're passing is not really actually all the elements of the array. You're just passing a reference. This also comes into play if you explicitly have a reference variable. So you can actually pass a variable to a function by using a reference. Sometimes this is called an alias. So what you can do is you can pass a variable by reference by using an ampersand. What will happen in this instance is that A will not be a copy of the first variable passed into this ref function. A will instead be the actual piece of memory. It will be the actual integer passed in, not just a copy, not just a value. Whereas in this case, C will be the actual value. So if we do something like we change both of these values to 1 and 2, A being 1, C equal 2, and then I call this function down here with two different variables. Let's see, B equals 3, D equals 5, and then I call this reference function on BD. Then what you expect to happen is that B will get changed from 3 to 1, and D you think might get changed to 2 because the function says C equals 2 here. It's not actually going to get changed to 2. Instead, D will keep its value. D will stay 5. And this is the effect of pass by value and pass by reference. And so if I output B and D here, D will be unchanged, and B will actually change from one to the other. We'll put a little space there. I don't think you guys can actually see the output today. I'll go ahead and try to run it one more time. Do you see that? No, I don't think you guys are capable of seeing this today. So it asks me how many names I want. I say 1, I wrote doc, and then the answer that it outputs is 1 space 5. So D was unchanged, but B was changed to 1. And the reason it was changed to 1 is because we didn't actually pass the value of B. We passed a reference to B. So call by value, pass by value, and call by reference or pass by reference, depending on the nomenclature that you read, can be very, very powerful to do kind of some interesting things. Often they're used in old C code to kind of pass, not C code. C code would just use the pointers. They're often used in other types of code to pass whole structures into some function so that the function can fill them out without having to recreate the function or copy the function as a return value or anything like that. Since we have a couple of minutes over usual time, it's also important to note that you can create a function which calls upon itself, and that's called recursion. If you've ever heard of induction or proof by induction, it's very, very similar to proof by induction. And what you do in recursion is you can have a function that is completely based on itself. So if you take something like the Fibonacci sequence, where the nth value is based on the previous two values, so f of n is equal to f of n minus 1 plus f of n minus 2, like this. What's really cool about this is that we can more or less just program this in a straightforward way. We don't have to convert this into a while loop or anything like that. Once you get a little bit handy with recursion and you see problems stated recursively, they become really, really quick to implement. I don't think it's going to be particularly beneficial for something like Fibonacci. You probably won't get a lot of value out of that, but you will get more value out of it once you start learning about trees and other dynamic data structures. So in order for this Fibonacci sequence to work, we have to know what the base cases are. It turns out that the first two Fibonaccis are 1, Fibonacci numbers are 1, and then the other Fibonacci numbers are just the addition of the 2. And so if we were going to implement this function, it would be a function that returns an integer because all the Fibonacci numbers are integers. It would take some integer n because it's the int Fibonacci number that you can see here. And then you would need base cases. So if n is 0 or n is 1, then you're just going to return the nth Fibonacci number of 0 or 1, which is 1. And then if it's anything else, if n has any other value, then we're going to just return this sequence up here. And you might say, hey, what if n is negative? If n is negative, then that's kind of an error case. So it might be important to kind of say, all right, the value has to be greater than 1 for us to actually do this recursion. And what I want to return from this function in that instance is just the function called on itself. This may seem like there's no possible way that this will work. But if you trace down what's actually happening on the function stack when you do this, it works beautifully. Try it for f of 2. So f of 2 is equal to f of 1 plus f of 0. And then f of 1 and f of 0 both return 1. And thus f of 2 is going to return 2. Take that knowledge and try to do f of 3. And you'll find that this works beautifully. Since it is possible for the user to ask for a negative Fibonacci number, which doesn't make a lot of sense, we should make some final return value here which handles that. And I can do something like return -1 to make that happen. So that's what I've got going on there. To actually see this work, maybe you want to do something like output the first 10 Fibonacci numbers. Okay, so I'll do that. I'll make a little for loop to output the first 10. Heck, let's do the first 20. Why not? Fibonacci numbers and see what that looks like. Let's go ahead and run that. And it's asking me how many strings I want. And then it outputs them. Oh, you guys cannot see it today. You're going to have to actually try this program and see the results today. But it spits them all out. Do something like 40 for your for loop and see what you get for that. Or if you really want to push the envelope, try 60 and see what happens. What does happen is because we're using a form of naive recursion, it makes things kind of interesting. Okay, I think that is all I want to tackle today. I hope you learned something. Go try out some dynamic arrays. They can be a little more powerful than the static arrays. There is some side effect computationally. The static arrays are going to be thrown on the stack and they will lose scope when normal variables lose scope, whereas the dynamic arrays kind of exist beyond the curly brackets. They kind of have unlimited scope. And because of that, all of your news should eventually have deletes. And what this does is it deallocates the memory that you have requested. And so in this case, since I had a string star names equals new, then I should at some point call a delete bracket names. The brackets are because I asked for an array. If names was not an array of values and it was just, say, a single string that was dynamically allocated, then I would be deleting these two brackets. But since names was an array, the brackets go. There's much more to talk about in pointer land. This is just scraping the surface of things that you can do. The most common thing that you do to start out is make these dynamic arrays so that you can have arrays that are determined by some computation or by the user, but otherwise their size is allowed to be determined at runtime. I think that's all I've got for today, so hopefully you learned something. If you have any questions, leave a comment. All right, thanks. Bye.